All right, I think it's 2 minutes past 8 in the morning in KL here, so it should be 10 in Brisbane time, and is it 6 in Canada, Richard? I think so.
Uh, it's 8 o'clock in the evening,
Oh,
and I'm still wide awake.
I mean, thanks for joining in the evening at your time. It's a bit late there. Yeah. Uh, but let's kick off the webinar. I think you can see my screen, and good morning or afternoon, evening to everyone that joined the webinar. Thank you for joining the webinar 35, which is the second webinar of ACIGS this year. I'm Sue, the Secretary of ACIGS. Today we have Dr. Richard Bathurst with us here, and he will be speaking about the role of geosynthetic stiffness in soil reinforcement applications. But before we go through his presentation, spare me a few minutes to have a quick introductions about IGS and ACIGS. So IGS is a global society with about 44 local chapters globally, with more than 4,000 members, including corporate members, individual members, and also students members. Our chapter is located in Australia, which covers the Australasia region of Australia, New Zealand, and Pacific Islands. So to join the society, you can either join the local chapters like in Australia. We have our own chapters that you can join through their website, or you can also log into geosyntheticsociety.org. On their website, you'll find all the information related to geosynthetic societies, from technical committees for different application, local chapters informations, events, where you can find the calendars for any upcoming conferences or events. So digital library is probably the most useful perks, in my opinion, on the website when you join IGS. So it includes proceeding of past conferences, videos, technical documents, and access to extremely reputable geosynthetics journals. So Australia is home to Australasia chapter for IGS, or in short, we call it A6. So we have our own chapter websites, which is acigs.org. So all the information of the chapters, from membership informations, from webinars, events, for roadshows, conferences, are all on the websites. And probably the important tab that you wanted to go into the website is the resources. So we have uploaded more than 30 webinars that we have hosted for the past few years on the website, with a lot of interesting topics being discussed. So do check out the website. It is free to access the webinars, and everyone can access the webinars as well. And if you have a requirement to have a certificate of attendance, please do email info.a6.org. You're able to get your certificate of attendance. So today's webinar is presented by Dr. Richard Bathurst on the role of geosynthetic stiffness in soil reinforcement applications. A quick introduction of Dr. Bathurst is he's a professor emeritus of civil engineering at Royal Military College of Canada, where he has taught since 1980 and hold a cross appointment in Queen's Universities. So he's the past president of a few engineering societies, including the International Geosynthetic Societies and the North American Geosynthetic Society. So Dr. Bathurst has authored and co-authored more than 200 journal papers and 250 other contributions. So he is the editor-in-chief of the peer-reviewed technical journal Geosynthetic International, and associate editor of the International Journal of Geomechanics and Geotextile and Geomembranes. So he is the fellow of the Canadian Academy of Engineering, the Engineering Institute of Canada, and the Canada Society for Civil Engineering. So Dr. Bathurst was also elected fellow of the Royal Society of Canada in 2017, which is the highest academic honor in Canada. So the Richard Bathurst Lecture was recently announced by IGS in recognition of his lifetime contributions to the development of geosynthetic soil reinforcement technologies and also the missions of the IGS. So the lecture will be delivered in the Quadrennial International Geosynthetic Conference, which is happening this September in Italy. So if you are present there, or if you are interested to join the ICG, please do look into the IGS website. So I'll pass the screen back to Dr. Bathurst, and if you have any questions, please use the Q&A function, and you can post a question there. All yours, Dr. Bathurst.
Thank you, Sujong, and the rest of the team at the Australian chapter of the IGS for this opportunity. Of course, I would much prefer to be in Oz in person, but this will have to do. The topic of my presentation is one that has been the focus of much attention recently, and it has to do with the role of geosynthetic stiffness in soil reinforcement applications.
Dr. Bathurst,
Reinforcement, yes.
You need to share your screen again.
Oh, I'm very sorry. Did you hear me? Yeah, just a sec now.
Yep.
Okay, I thought I was already sharing. I thought you had to turn me back on. Excuse me while I fumble around here.
Sorry about that.
One moment.
Yep, no problem.
Oh, there we are. Okay, share. There we go. There we go. And there we go. And
yep, all good.
Okay. So this was my title slide, the role of geosynthetic stiffness in soil reinforcement applications. And like I mentioned, this is a topic of great interest to me, and I'm happy to have the opportunity to share my thoughts on this topic with my friends in Australia. By way of introduction, I'm not sure that I have to say much to this group, but reinforcement geosynthetics are used in many geotechnical applications. These include mechanically stabilized earth walls, MSE walls, slopes, reinforced embankments, reinforced piled embankments, reinforced fills over voids, and paved and unpaved road foundations. Reinforcement stiffness. Well, analytical and numerical models for the analysis and design of reinforced soils under operational conditions, that is serviceability conditions, often require an estimate of the equivalent linear elastic stiffness of the reinforcement. And examples of this are computing the tensile loads in MSE walls under operational conditions, predicting or estimating the facing deflections of MSE walls, the loads and strains in the reinforcement for reinforced fills over voids, and the problem of a reinforced granular layer over a very soft foundation. Now, it's important to make a distinction between serviceability conditions, operational conditions, and ultimate limit states. When we speak about ultimate limit states, then we're analyzing or designing a structure against failure mechanisms, which are coupled with estimates of adequate margins of safety. And under these conditions, we need to know the tensile strength of the reinforcement. Under operational serviceability conditions, we are not expecting the reinforcement strength to be exceeded, i.e. the reinforcement to rupture or yield. But we do need to know what the load in the reinforcement is. And this load is a function of the stiffness of the reinforcement, the strain in the reinforcement, and not its strength. The challenge is that reinforcement geosynthetics are rate-dependent materials. This means that their load strain properties are load, strain, temperature, and time dependent. And this makes the selection of stiffness values to be a challenge and to be carefully considered. And I can demonstrate this by looking at the results from some constant in-air tensile tests. And what you see in the photograph on the right-hand side is a conventional in-air tensile test apparatus, and it's showing a uniaxial HTPE geogrid. In North America, the standard test is carried out at 10% strain per minute. And if we look at the top red trace in the plot on the left-hand side, that shows the load strain response of this particular material at 10% strain per minute. If we speed up the test, then we can see that these other curves, and you can see that the material is exhibiting a stiffer response. If we perform the same series of tests on a polyester material, the rate effect is less for these materials. They also have a different shape, typically a sigmoidal or S shape. But over the low strain levels and low load levels that we assume are of interest under operational conditions, you can see that these curves are showing a sort of a similar strain hardening type of shape. The most common approach to quantify rate-dependent properties of these materials is to carry out constant load creep tests, as illustrated in the photograph on the left-hand side. Although today also stepped isothermal methods are also common. But let's stick to these simple constant load tests for simplicity. These specimens are subjected to constant load, and the strain under constant load is recorded against time on a log scale. And what we expect is that as a sample is subjected to a higher load, then these strain log time curves shift upward, as you can see through this set of curves on the right-hand side. And these specimens will go through primary, secondary, and tertiary creep to rupture if the load is great enough and the load is left in place long enough. Under operational conditions, again, we're interested in strain levels and load levels that are at the low end, and the material remains in a primary strain mode where we wouldn't expect the material to strain to rupture. So the objectives of this lecture are to introduce the concept of geosynthetic stiffness, describe a simple two-component isochronous stiffness model to reproduce rate-dependent behavior, show some model results, and demonstrate the use of the model in 3 different reinforced soil applications. So let's talk about geosynthetic stiffness. The slide on the left-hand side we've seen before. These are these constant load creep tests. And what we can do is through these tests, we can take time slices, which you can see by the symbols. And using these values at the same time, we can construct isochronous load strain curves as shown on the right-hand figure in this slide. And these isochronous curves and the notion of isochronous load strain curves is not new. In fact, we can trace their use back to the 1980s with the work of Alan McGowan at the University of Strathclyde. Now, superimposed on these isochronous load strain curves is the constant rate of strain test at 10% strain per minute that I mentioned before. And what you can see is that as the isochronous curves, the isochronous times increase, this constant rate of strain test falls more and more above these isochronous curves. And it's quite clear that these type of tests cannot be used to capture the rate-dependent behavior of these materials. The secant isochronous stiffness at particular load and strain is simply the slope computed at load T and strain, as you see here. If I can find an equation for the isochronous stiffness for each isochrone, I can compute the tensile load at a given strain and time, with time matching that isochronous time. And equation J is called the isochronous secant stiffness. And the question then is how can I find the form of this equation? And this leads to the development of a simple two-component isochronous stiffness model to reproduce rate-dependent behavior. So after connecting these points on an isochronous curve, we can then construct a secant isochronous stiffness curve as shown on the right-hand side. Okay, so each one of these points has a slope, and at the same strain, I can then plot that slope on that particular isochronous curve, and this gives me an isochronous stiffness curve. And a two-component model of hyperbolic form can be used to capture that trend quite nicely. And this formula, as you see it here, has two components. One is J naught, which is the intercept of these curves with the vertical axis. And the chi term that you see here is a quantitative measure of the magnitude of the curvature. So once we have this equation for each of these isochronous stiffness curves, we can then put it into an equation where the stiffness, the secant stiffness times the strain, will give us the load that is predicted at that strain and that time. Now, to find these parameters, my PhD student, Fahimi Nafchali, collected more than 600 constant load tests. And these are high quality tests. A lot of them were from the AASHTO NT-PEP program in the United States. All of these tests were carried out in conformity with appropriate ASTM standards. There were 89 different products and 7 product classification types. So these data fell into different categories, including high density HDPE geogrids, polyester PET, woven and knitted geogrids, polypropylene, punched and drawn geogrids, and et cetera, including even PET strap reinforcement products. So what you see on the left-hand side are a series of load strain curves for a polypropylene geogrid. And using the procedure that I mentioned to you before, we constructed the secant isochronous stiffness curves for this data. And you can see that for each isochronous curve, there's an intercept, which is the J naught term, and the chi term is a measure of the curvature of these stiffness curves. And in the shaded box, you can see the numerical values for those two parameters. And it's interesting, you can see that as the strain in these curves increases, and time increases, these isochronous stiffness curves tend to converge as well. But when you're operating at very low strain levels and low time and short times, you can see there's quite a big range of stiffness values that can be computed. Also, you can see again that I have put on both of these plots the 10% constant rate of strain test result. You can see how that test result is falls above almost all of these curves on the left-hand side, and you can see also that the computed stiffness curve is also well above the isochronous times at healthy periods of time. In this case, more than 10 hours. So again, the take-home lesson here is that just blindly using a constant rate of displacement or strain test will overestimate the stiffness of the reinforcement, sometimes by very large amounts. This slide shows another material. This is a PET woven geogrid. And again, you can see on the left-hand side, the isochronous load strain curves at different hours. You can see the constant rate of strain test, again, falling well above those curves. And then from this data, this 2-parameter isochronous stiffness equation has been fitted. Again, intersection points are shown here. And you can see that as time and strain increases, they do tend to flatten out. And again, in this box that you see here shaded, those are the extracted J and chi values for this particular product. And again, we did this for almost 90 different products. And this data has been published in this paper that I referred to earlier in 2021 in Geotextiles and Geomembranes. And this slide shows some trends. Here we have plotted the stiffness curves, and if you focus for a minute, because it's a busy slide, if you focus on the red curves, these are curves that have the same J naught term value, but they have increasing decreasing values of this chi term, which means they're creepier. So as this chi term increases, you can see decreases rather. You can see how the curve is becoming more pronounced, indicating a product which is more creep susceptible. We have collected this data, and some interesting summary plots have emerged. So for example, on the left-hand side, you can see data points for the values of J naught and chi for an isochronous time of 1,000 hours. On the right-hand axis, we're plotting these values directly. Sometimes it's convenient to invert this parameter so that when this parameter is infinitely stiff, it approaches a value of 0. Now, most products have a curvature value which is positive. And what we see here is that as for the same J naught term, we can see that as this value of chi t, or the inverse of chi t, changes, we get completely different shapes. And the nice thing about this model is that when chi t is very large, effectively what you're modeling is a linear elastic material. So this model can actually be used for very stiff, inextensible reinforcement. It's not just confined to extensible polymeric materials. And when you look at all of this data together, what you can see is, sort of if you had to pick a single pair of values, perhaps for parametric analysis, a typical J naught value is somewhere around 1,000 kilonewtons per meter, and the curvature parameter is, somewhere around 90. But you can see that there is a range of these materials, and we know what these values are from this database that we have generated. And we were able to use this database to carry out parametric analysis of different applications, which is what I'm going to show you later in my presentation. When we examined this database, we noticed some trends. And what we found was, and not unexpectedly, that if you plot the stiffness of a reinforcement, the secant stiffness value, what you'll find is it generally it increases with the ultimate strength of the material. And I think that is not contradictory to our intuition. And in fact, we found that we could come up with linear relationships between the secant stiffness and the ultimate strength for products. In some cases, a better fit was between the stiffness value and a power function of this form, okay, depending on the material. So for a particular class of material, for example, if we're talking about HDPE geogrid, when we take all of our data for that material together, a useful approximation is that the stiffness of this material is about 6 times the ultimate strength of this material. And similar coefficients of proportionality are available for other classes of material. If you take all the data together, then and we can call this pooled data. Then there's a linear relationship again, and that coefficient of proportionality is about 5. So you ask yourself, so what? Well, the thing is, this high quality constant load creep test data is not always available, but we always have the ultimate tensile strength of the material available. So if you know what that is, you can use this pooled value of 5 times T alt as a rough estimate to estimate what is the stiffness of the material. If you know what the product classification is, you can get a tighter approximation. And if you actually have product specific creep testing, of course, you can use that data directly. So here you can see is just the highlighted portion in red here. Again, shows the relationship between the secant stiffness of the material and T alt taken directly from a constant rate of strain test. And you can see that this curve gives you a coefficient of proportionality for pooled data, which is higher. For this this in-air constant rate of strain test, which is greater than the pooled data result, which again shows you that these constant rate of strain tests have to be used with caution because they're going to overestimate the stiffness of the material. So getting back to that point, if one wants to think about the estimate of the reinforcement stiffness, from a sort of uncertainty point of view, if you have product specific data, in other words, you've gone to the time and expense to carry out constant load creep tests or other forms of creep testing, the variation in your estimate of the stiffness of that material might be about 6%. If you know that your material is part of a a class of materials of one type or another, then when you use this approximation that I showed you before for this linear approximation, then your estimate of the stiffness might be will have a COV of say 20%. And if you just lump your product in with all the other data that we've got, then the uncertainty is about 27%. So this demonstrates that there is a practical benefit to actually carrying out product-specific creep testing, because you are rewarded with a better estimate of what that stiffness is. And nowadays we are moving towards probabilistic or reliability-based design methods, and these types of estimates of uncertainty in input parameters becomes very important. And so this type of data is progressively being used in reliability-based design. And if you do reliability-based design and you have your actual product-specific data testing at hand, you are going to be rewarded with a more accurate estimate of the stiffness of the material. And it actually turns out that you'll end up with a more cost-effective solution. But probabilistic design is beyond the scope of this particular lecture. So let's look at some example applications where stiffness matters. And the first example that I'm going to show is one in which we want to estimate what are the out of alignment wall profiles for a wrapped face MSC wall. So you see on the right hand side, you can see this idealized schematic of a wrap face wall. And there are some solutions in the literature, including one by Jewell and Milligan, where you can calculate for each soil layer with a reinforcement layer in the middle of it, what its displacement will be after it has been put in place. So this delta H is just the incremental displacement of that soil layer. And it's computed using this equation that you see here. And what you see is that this parameter J, which is the secant stiffness of the reinforcement, will play obviously an important role in this calculation. The rest of the terms are largely familiar. There's an active earth pressure coefficient, soil unit weight, coverage ratio, whether you've got 100% coverage of the soil layer going into the slide, soil dilation angle, and soil peak friction angle. So if I have those parameters and I use this equation, then I can generate plots on a project-specific basis, as you see here. So what you're seeing on the horizontal axis is the horizontal displacement of the wall at the end of construction. And the vertical axis is just the height above the toe. And these plots all have a similar shape, but you can see that as the reinforcement becomes stiffer, the deformations at each elevation are less. And I think this is fits our intuition. I have also plotted in this figure in the gray zone the range of values of displacement that have been specified or expressed as expected values in various research papers and in codes and guidance manuals. So you can see there's a large range of displacements that we might expect for a wall of this height, and whether we're in and out of that band will depend very, very much on how stiff the reinforcement is. Now you saw in the previous slide that there are other parameters involved in this calculation, including the friction angle of the soil. So one can carry out a parametric analysis and come up with design charts such as the one that you see here. So the vertical axis on this figure is the normalized maximum out of alignment of the wall at end of construction, and it has been plotted against the creep stiffness of the material and also the friction angle. And you can see that both stiffness and friction angle have an effect. But if you to stare at this plot long enough, what you could convince yourself is actually the stiffness is a much is more important than the friction angle. The other thing that you can see on this plot is that the horizontal axis on the top of the plot is actually the ultimate strength, because a reasonable relationship between the secant stiffness and the tensile strength is a factor of 5. So this increases the utility of this chart. In case you don't have the creep stiffness value, you can estimate what it is using a pooled data, where the stiffness is about 5 times the ultimate strength. Now, we can also extend this problem to how can we estimate what the maximum reinforcement loads are in these reinforcement layers. And to calculate the reinforcement loads, I can use the stiffness method, which appears in the AASHTO code in the United States. And when you unwrap the equation for the maximum load in a reinforcement layer using the stiffness method, it looks like the equation that you see here. And you can see that the maximal load in the reinforcement is related to the magnitude of the stiffness of the reinforcement, plus a whole bunch of other things, of course, like the spacing of the reinforcement, SV, the height of the wall, and some other parameters that I won't get into in great detail. So from this equation, and knowing what the strain is, which we got from the last chart, we can calculate. We could also calculate the strain, as we showed before, knowing what the load in the reinforcement is and the stiffness and the coverage ratio. So this is for a wrap-faced wall, and we can take this data and we can make some more plots, as you see here. So what you're seeing on the horizontal axis is the maximum load in each reinforcement layer. And the vertical axis, again, is the height of our calculated point above the toe. And as the stiffness of the material increases, the loads increase. And as the stiffness increases, the strains decrease. And I don't think that this is unexpected, conceptually. But what is very interesting from these plots, and this is a signature feature of the stiffness method, is that the distribution is bilinear. The loads in the reinforcement tend to increase linearly with depth up to a point, and then they become more or less constant. And this sort of bilinear trend is actually consistent with what's been observed in instrumented full-scale geosynthetic reinforced walls in the field. And the nice thing about this plot is it allows you to examine the maximum strain, because you don't want the strain in the reinforcement to become excessive. And in fact, in the stiffness method, if the strain in the reinforcement is greater than 3%, that means your soil has actually failed. And if you want to keep this structure at working stress or serviceability conditions, you need to keep the soil strains down which means you have to keep the tensile strains in the reinforcement below a critical, for example, 3% strain value. If we again look at what would happen if we used say the simplified method. The simplified method is, well, sometimes known as the tie-back wedge method, and this is a classical method for estimating reinforcement loads, but it depends only on the strength of the soil. It does not reflect the stiffness of the reinforcement. Now, sometimes you might get lucky, and this method may predict reasonably what the loads in the reinforcement are for very high, stiff reinforced soil walls towards the top half of the wall. But once you get below about the bottom half of the wall, this method tends to overestimate the loads in the reinforcement and therefore is excessively conservative. And again, using this simplified method, you have no idea what the strains in the reinforcement are. And this may violate, your serviceability or operational condition criterion. Another example where stiffness plays a role is the problem of a reinforced granular fill over a void. So the scenario is that in an area where you might be anticipating some karstic topography where a void might form after, say, a road embankment has been placed, or maybe you're in a northern area where you're having permafrost melting, or maybe you have a situation in which a void is formed due to soil washout, due to a pipe failure or collapse of a mine working, whatever. There are lots of scenarios that you can imagine where a void could happen, and the problem is that this could cause the embankment to locally collapse. So a strategy is that in these types of terrains is to place a reinforcement layer near the bottom of this fill in order to mitigate against foundation collapse. So for example, let's keep things simple and imagine that we have a long void. That means a trench-like void extending into the slide, and it has a width of B. There are solutions available in the literature to calculate what the maximum load and strain will be in that reinforcement layer for a particular scenario. And depending on which method you use, one can develop a design flow chart. Now, this flow chart is based on the method of Giroux et al. And the way that this flow chart operates is that it recognizes different limit states. So for example, if we assume a void of width B and a deflection of depth D, we can calculate the deformation and strain limit states for that condition. And you see this equation here for E max. And then knowing that value, we can then calculate what is the maximum load in the reinforcement. Again, there's an equation for that. It basically satisfies limit equilibrium and assumes that the deflected shape is an arc of a circle. And this limit state would be exceeded if this maximum load exceeds an allowable load. Okay, whatever you decide that should be, it might be 1/3 of the ultimate strength. So if you don't satisfy that this relationship, then you have a strength limit state failure. Once you have established what the load is, you can then calculate what is the mobilized stiffness in the reinforcement. Because in order to sustain the maximum calculated strain and the maximum load, the material itself must have enough stiffness. So this is the stiffness limit state. And this has been, a primary contribution of our work with respect to the problem of a reinforced fill over a void. So each reinforcement material has an available stiffness. We have just talked about that. And in order not to fail the stiffness limit state, the mobilized stiffness must not exceed this value. And again, if I don't have product specific data, I can estimate what that available stiffness is by finding the coefficient of proportionality between secant stiffness and the ultimate strength of the material. And that'll at least get me into the ballpark in order to look at this particular limit state. And the thing is, there are, depending on which method you use, of which there's about 4, you can construct these flow charts and evaluate each of these limit states. And if you, in the paper by Neftali and Bathurst last year, we provided those flow charts for different design methods. So here is a chart that sort of summarizes some of the points that I've just made. When you use this method, you have to assume a ratio of reinforcement deflection at the void, normalized with the void width, and that gives you a strain curve that you see here. Knowing what this strain curve is, you can now find what the mobilized stiffness is, because you have the strain and you have the load, and this is the mobilized curve. And what you do is you make sure that that mobilized stiffness doesn't exceed what's available to you. Now, those models that I've shown you up to this point have been analytical types. But the stiffness is also important if one uses a more sophisticated approach for these complicated soil structure interaction problems. And this means numerical models based on finite elements or finite difference. In this particular case, we're looking at the problem of a reinforced granular fill over a very soft foundation soil. So a granular fill is typically placed over these materials so that you can work on the site, so that you can place the footing, and that this footing, the loads and pressures developed by this footing will be dissipated over a larger area of the soft material. And what's of interest is, well, if we put a geosynthetic reinforcement layer near the bottom of that granular layer, what further improvement in the load displacement response to that footing might I realize, if anything? So this is an example of a recent paper that, in fact, it just came out a few weeks ago, where we investigated this problem and this question. So this is a FLAC grid, and the soil that we were looking at here was a soft to very soft material, which means 5 to 25 kPa undrained shear strength type of material. And in order to model this material in a FLAC code, we had to take the secant stiffness formulation, which we've seen before. You can see the left-hand side here is the stiffness curves. Here is this secant stiffness formulation that I was explaining. But in a numerical model, you don't want the secant stiffness. What you want is the tangent stiffness formulation, because in these models, these models are solved for incremental strains. And so you have to differentiate this formulation that you see here and turn it to a tangent stiffness formulation that you can then embed in your numerical code. And here's an example. What you see on the left-hand side is a footing which is being pushed into this foundation system. And the contours that you see there are the vertical displacement settlement contours. And you can see the trace of the reinforcement layer in red here. On the plot on the right-hand side, you can see the bearing pressure that was applied to the footing and the resulting normalized settlement on the bottom and the true settlement at the top. So without the presence of the granular layer, the red trace emerges, and in fact, the ultimate capacity is coincides with the classical Prandtl solution. If I then perform the same experiment, but I put a layer of granular soil, about 1/2 meter on top of the clay soil, then I get this solid black line that you see here. And then if I repeat the experiment with progressively stiffer reinforcement geosynthetics, then these curves start to diverge. There's about a 40% improvement between the no granular layer case and the granular unreinforced granular layer over clay, and then there's incremental improvement thereafter. But probably from a practical point of view, you can argue that there's really not that much improvement, particularly if you're operating at, say, a 25 millimeter serviceability criterion, which is not unusual. You can find in the literature sometimes that people will adopt a 75 millimeter or 3-inch settlement criteria, and there you could see perhaps some practical benefit. But again, remember that reinforcement material does some other things for you that are hard to quantify. For example, it'll help you get onto the site and to place the granular soil as well. So there are some benefits. They're just sometimes not easy to quantify. So here, this is just a sec. Yeah, so this slide is showing the effect of the curvature parameter. So here we've frozen J0 at 1,000, and we've just played around with the magnitude of that curvature parameter. And basically, as the material becomes less creepy, the curves become move vertically up here, which is not surprising. So a very creepy material, you have less capacity than a material which is becoming closer to being inextensible, at least with time. And the other games that we were able to play was, okay, so we're interested in, the pressure settlement response, but what about what is happening to the reinforcement itself? So here we are with a material where it essentially doesn't have any curvature in the secant stiffness curves, and we're just looking at the effect of J0. So this is the maximum load in the reinforcement on the vertical axis, and then we have displacement on 2 axes in the horizontal direction. And the red trace is a typical reinforcement with a J0 value of about 1,000. And you can see that as the stiffness increases, the load in the reinforcement is increasing as well. In fact, if you look at these numbers, you can see that there's about a threefold increase in the maximum tensile load in the reinforcement as we go through one order of magnitude, from 300 to 3,000 kilonewtons per meter. So the stiffness does play a role in the loads and obviously the strains that are going to be developed in the reinforcement. And here again, we freeze the J naught parameter and just play around with the curvature parameter. So again, what you find is the loads in the reinforcement are less at every settlement level for the materials that are creepier than the less creepy materials. And again, this doesn't surprise us. From a practical point of view, what you see here is we have recognized that J is about 5 times T alt, and this means that we can calculate what is the mobilized strength in that reinforcement. And you can see that the maximum mobilized strength is only about 6% of the ultimate strength. So this material, even though it's generating tensile load in the reinforcement itself is not under a load level that would make us worry about whether it may fail in rupture. And along that theme, we can also look at the distribution of load below the footing. So we have 2 plots. The one on the left has a chi value of 100 kilonewtons per meter, and the chart on the right, sorry, that's the left side, right side, has a chi value of 10 kilonewtons per meter. And the first thing you can see is that the maximum loads in the reinforcement layers for the same undrained shear strength are higher for the materials that have a higher curvature parameter. You can see this scale is topping out at 30 kilonewtons per meter, and this one's topping out at 10 kilonewtons per meter. The trends are pretty well the same in both cases. You can also see that the loads in the reinforcement, regardless of the actual set of stiffness parameters, is actually higher at the edges of the reinforcement than at the middle. And of course, this difference will depend on the width of the footing, and it will also be influenced by the thickness of the granular layer and also by the strength of the clay foundation, obviously. And it's actually what we found from this analysis is that the strength of the foundation clearly plays a major role in the magnitude of the load that's in the reinforcement. Now, the problem with returning again to this reinforced granular fill over a long void, the problem with these analytical solutions, which are captured by this diagram that you see at the bottom of the slide, is they're very simplistic models. They really can't truly capture the interaction between the soil, the reinforcement, and the like, because these are coupled problems. The only way that you can gain insight in this regard, at least numerically, is to carry out a numerical modeling with, for example, say FLAC. FLAC happens to be our favorite program. And so what you see at the top of this slide is a numerical FLAC grid, which is simulating the problem of a void which is 2 meters wide with a reinforcement at the bottom of the granular layer. And what one can do is do all sorts of parametric analysis to see, what are the effects of all the input parameters of a problem of this type, the void width, the height of the fill, this type of thing. And this is what my graduate student has been working on recently. So what you see on the left-hand side is a plot of the surface deflection. This is actually the deflection at this point here versus location along this domain. So the middle of the void is right here. And what you can see is as the reinforcement becomes stiffer, the deflection goes down. I don't think this is unexpected, but the point is you can't get this quantitative appreciation from an analytical model. And on the right-hand side that you see here, this is the load in the reinforcement. And again, as the reinforcement becomes stiffer, the load in the reinforcement goes up. Okay, and this is of interest to us because we're interested in a strength limit state calculation or appreciation of this problem. So from the collection of slides that I've just shown you and our own work, there's a couple of takeaways from this work and the influence of stiffness. The first one is that under operational conditions, it is the stiffness of the reinforcement that is important, not its strength. And this is a bit of a paradigm shift for us poor geotechnical engineers who were raised on the milk of Rankine and Coulomb. But under operational conditions, it's not true. Structural engineers understand this, and yet we're a little bit slow in adopting that intuition in our own soil structure interaction problems. If we use rapid in-air tensile tests, we'll overestimate the reinforcement stiffness required in analytical and numerical solutions. So it will be unsafe for design. On the other hand, when we want to estimate MSE wall deformations, we'll underestimate the deformations, and the tensile loads will be overestimated. A two-component hyperbolic isochronous load strain model is now available to characterize reinforcement stiffness, and a large database of values is available. From this database, we can appreciate that if you can do product-specific creep testing, you will get a more accurate estimate of the stiffness parameter, and therefore your models, either analytical or numerical, will be more accurate. If you don't have this data, there are some convenient approximations that relate stiffness to the ultimate tensile strength of the material, which is something that we always have from the manufacturers and suppliers. So if any or all of these topics are of interest to you, there are some papers that have been published by my group. I'm also citing the paper by J.P. Giroux, which is one of the example design methods for the reinforced fill over void problem that I talked about. These are all online. And finally, I want to just recognize the contributions of my PhD, Fahima Nafchali, who will probably graduate this summer, much to her relief, and also my friend and current visiting postdoc, Reza Jamshidi Shanari, who has been a great partner in these various projects. So thank you for your attention. And I don't know what's left in the program, but certainly if there's time, I would be happy to answer any questions. Thank you very much.
Thank you, Dr. Bathurst. Really insightful present. I think I managed to get into some of these papers to really understand further on the details. Yeah. For those of you that are still online, if you have any questions, please do post it on the Q&A sections. We are a little bit over time, 7 minutes over time, that maybe we'll get 1 or 2 questions, and if there are more, then we will actually send it to you personally. So, Dr. Bathurst, there's one question from Jonathan Shamrock.
Yes,
Could the Juru
I can see it.
Yeah, could
Yep,
the Juru
I can. Yep.
be used for the design?
Well, excuse. In fact, one of the examples that Dr. Giroux gave when he developed his method, part of the motivation was the problem of a liner cover system, for example, that might be suffering some differential settlement. So sometimes they put a geogrid under the liner to make sure that the void doesn't cause it to strain to rupture. You could also put it at the bottom of a liner system, but I would hope that anybody that's designing a landfill would not put it in a place where there's any possibility of a void forming. I think a good place for this, and where I've seen it used quite a bit, is in Germany, where they have karstic terrain and they have highway embankments, etc. And they'll put these geogrids down below these thin embankments as a method to mitigate against collapse of the embankment or and even the expansion of a void. And what they'll do is, you'll get a bump, but then they know the void has been filled. They know where it is, so excavate the fill the void up, and then replace the reinforcement and the fill. This is what I've heard by people that are in the real world. The stiffness calculus. Okay. Just a second. The second question from Gordon Steve. This is a very insightful question, and we've done a lot of work, and I mean historically over the centuries, where we've looked at the effect of installation damage on the stiffness of reinforcement. And it's very interesting that you really have to damage these materials before you generate substantial changes in stiffness at low loads and low stiffness. This doesn't mean that you don't reduce the tensile strength. Okay, I mean the ultimate tensile strength is more sensitive to damage than the low strain, low load stiffness of these materials, thankfully. Okay, so there's another. Can I keep going?
Yep, maybe we can answer one more questions before we end this. Yep.
Okay, so I'm looking at the question from Pakia Kumar.
Yeah.
If the reinforcement fails under ultimate load and void situation, does the reinforcement reach ultimate strain value or stiffness failure? Well, that's why you have to do. It's a chicken and the egg thing. If there was a flow chart that I showed you, and the first thing that you look at is you look at the strain level, and then you have to make a decision about whether that strain is high enough that the material will strain to rupture. But even if that criteria is satisfied, you could still get a situation in which the material is not stiff enough to sustain both the load and the strain. So you have to look at all of the failure criteria. Once you exceed a failure criteria, well, then the thing will probably keep on straining and rupture, maybe quickly. Okay.
Thanks for the answers. Hope that it's useful and insightful for those that are attending the webinars. We will end this webinar very soon, and the recording will be available a few days after. So if you still need to get to the details of the webinars, please go through the recordings. And also please go through the cited papers as well. I think those are really helpful. Lastly, thank you, Dr. Bathurst, for sparing some of your time in the evening for the webinar. And also thanks to the attendants attendees for attending the webinars. We'll have our webinar probably the next webinar in August, if I'm not wrong. So stay tuned on our bulletins and on our LinkedIn. Thank you, everyone.
Thank you very much.
Thank you. Yep. See you. Bye.
Bye-bye.